Hi everyone. These videos are going to be about the tutorial. Today, as per Google Classroom, we're aiming to get done questions 13 all the way to 2023, I believe. Just a bit of a reminder: these are questions relating to the first topic that we've done on waves and thermodynamics. So make sure you have your booklets around that we've been working on during class, and that would help you with some of these questions if you're stuck. General order is I'll read the question, maybe show some intuition about it. I'll get you guys to pause, have a go at the questions yourself, and then I will follow that through with a solution. And we'll proceed with the different questions. So let's get started. Okay, so question 13, it says, a sketch of a wavefront of a longitudinal wave is shown below. The wave is traveling to the right, as directed by the arrow. Okay, it says A, identify any letters or letter in the diagram that identifies the position of a compression. Okay, so let's have a look at that. So remember, a compression is the high pressure region in a longitudinal wave. So you can see here at C where all those lines which are representing wavefronts are clustered up together. They represent the compression phase of that longitudinal wave. Okay, then you got the areas here more spread out. There are a refraction phase, and somewhere in between here, that's supposed to represent normal atmospheric pressure. Okay, as you get to this point F, you can see that we're almost beginning a compression, but we're not entirely there yet. We've just begun the first part of the compression. It's almost like we've gotten to just about to get to the peak of a crest in a transverse wave, but we haven't completely done that peak, so we can't count that as a compression. The same thing is happening in A. Okay. For question B, it says, identify the letters in the diagram above that identify the positions of a refraction phase of a wave. So I'll get you guys to have a pause the video, have a go, and we'll go over the answers. Okay, so for question 13, A, you should have gotten the only place that is experiencing a compression is region C, and for B, the places that are experiencing refractions are at position that are denoted by the letter. If there was a letter here, we could say there was another one occurring here. It's just A. Okay, let's move on to the next question. Okay, question 14, it reads, propose an example of a longitudinal wave. Describe how it transfers energy from one place to another, and analyze the movement of any particles associated with the wave. Have a go at this question, and then we'll write a response together. Okay. Question 14. Now remember, longitudinal waves are generally just mechanical waves that apply to sound waves. You can also see them a little bit in seismic waves due to earthquakes. But the question here says, gives an example. So the example is going to be sound waves. So sound waves are a form of mechanical longitudinal wave. Okay. How it transfers energy from one place to another. Okay, so what happens is kinetic energy from some source vibrates and imparts some of its energy onto the air particles. Okay, and those air particles kind of like bumper cars, like hitting each other at the frequency of that source of disturbance, and that sound is propagating through the air like bumper cars constantly hitting each other. So the energy is imparted to the air particles. Okay, the air particles collide with each other at the frequency of the source. This allows for the sound wave to propagate through the air molecules / medium. Okay. Okay, let's have a look at question 15. Now, just quickly, it's supposed to be a HSC. You're supposed to be spending 1.5 minutes on each mark for a question. Now, some of these marks are questionable. Yeah, the top one, that's probably a 3 marks. That sounds justified, but the next one is not like that. It says, the term amplitude is used to describe an aspect of a wave motion. Recall a wave motion that you are familiar with and describe what is meant by the term. So have a go at this question and we'll go over the answer. Okay, so we can use any form of examples. It's a bit more complicated when we use a transverse wave, but when we use a longitudinal, but when we use a transverse wave, this becomes a lot easier. So we can model this as some kind of water wave, so and we know an amplitude is just the displacement from the center to either the peak or the trough, and the other way this is presented is half the distance between the crest and the trough. Okay, so let's have a look at that. So the amplitude in a water wave, could be a ripple, could be some kind of beach wave or something, is a transverse wave. Oh, sorry, that's not make sense. Okay, so water wave is a transverse wave, that's fine. Amplitude is defined as half the distance between the crest and the trough. Okay, and that's perfectly fine. Okay, let's have a look at question 16. It says, when light from the sun arrives at the surface of the earth, it warms up surfaces that it falls on. The best explanation for this is one of these, A through to D. Have a go at choosing them, choosing the correct one, and then we'll go over the answer. Okay. Let's have a look. So A says light particles have traveled from the surface of the sun to the surface of the earth. However, these particles transfer no energy. That's not the case. Otherwise, the sun will always be and will never balloon out and destroy itself at some point. So no, that's not right. B, light waves have managed to cross the nearly empty space between the earth and the sun by vibrating the few particles that exist between the earth and the sun. Okay, that's implying that light, which is an electromagnetic wave, requires a medium. Now remember, it's only mechanical waves that require a medium. Electromagnetic waves don't require a medium. Okay, C, light waves carry energy from the surface of the sun to the surface of the earth. They do not need a medium for transmission. Okay, that one could possibly be it. D, light from the sun does not warm the surface of the earth. The warming effect is from other mechanisms. That's completely wrong. So the best one is that. The only thing confusing about here is the word transmission. Now we've talked about transmission meaning light passing through some kind of transparent object, but here I think the word that should be written there is propagation. They do not need a medium for propagation. Just be cautious about that. Okay, let's move on to, so the answer for 16 is C. Let's move on to 17. Okay, it says, calculate the wavelength of the radiation emitted by a radio station called the Edge 96.1 or 96.1 megahertz. Take the speed of light to be 3 times 10 to the power of 8 meters per second. Okay, so this is, we're going to see what we know. Our knowns are the speed of light, which is given by the variable c, and that's 3 times 10 to the power of 8. We are also told that the frequency is 96.1. Mega is a prefix that denotes the power of 6 hertz, right? So they're asking us to find the wavelength, right? We don't know wavelength. So we can solve for wavelength using this expression. Now remember, we don't have v, we have speed of light, and because all electromagnetic waves travel at the speed of light, any electromagnetic wave that we have a frequency or a wavelength, we can solve for the other variable. They all travel at the same speed, which is speed of light. So this is written more appropriately like this: c is equal to frequency wavelength. We're solving for wavelength, so wavelength is equal to c divided by frequency. And we know c is equal to 3 times 10 to the power of 8. We know frequency is 96.1 times 10 to the power of 6. and we do that into our calculator. 3 times 10 to the power of 8 divided by 96.1 times 10 to the power of 6, we get 3.12 meters per second. Okay, let's move on. Okay, now question 18 we're not going to do because that's part of the old syllabus. So calculate angular wavelength, variable k. That's something that we don't do anymore. That's not calculated, and that's just the general equation where we plug in different values to solve for something. But we no longer do that question. So we'll go on to the next question. Okay, so let's have a look at this question. This one says, identify a transverse wave type that is used in everyday life to transfer energy from one point to another. Outline how the energy is transferred from one point to another using using this type of transverse wave. Okay, I'll give you guys a go, and then we'll come back. Okay, now a transverse wave can be both an electromagnetic or it can be a mechanical wave. I think we've talked about mechanical waves a fair bit, so I think a transverse wave would be good to consider. Now again, so here's our transverse wave. Now remember, an electromagnetic wave is a transverse wave, but it's superimposed. It's got an electric field going in one dimension, and at a second dimension it's got a magnetic field, and that's given by variable b. But it is just it is just a transverse wave, so it is generally just that. We just model it as that for simplicity. Okay, so there's our transverse wave, that's all good. And we're going to do an electromagnetic wave. So let's do that. I'm going to say microwave. So a microwave is created by moving electrons at certain frequencies. Okay, so when we do that, we create some microwaves. Now it depends on the intensity of those electrons. So if you move those electrons very fast and very sharply, you can get X-rays or gamma rays that are produced at a certain rate. Now I know with microwaves they have certain pieces of equipment which get those electrons clumping up and being moved at a certain speed to create these microwaves, and then those microwaves are channeled. So once we've got those microwaves that have been created by the moving electrons, what happens is they are moved through the microwave, and once they move through the microwaves, they hit molecules and make them speed up. So okay, microwaves in ovens transfer their energy to polar molecules like water by making them change their polarity constantly. So by doing that, by getting those particles, those water molecules to oscillate back and forth, so the oxygen end would be a negative and the hydrogen would be more like a positive end. When those electromagnetic waves hit it, those charges flip around. By flipping those charges around, that molecule is put to oscillate in between other molecules of water, and they heat up, so they gain the kinetic energy. Change the polarity constant, making them change the polarity. This imparts the microwaves energy in the form of kinetic energy in the molecules. That's what a microwave does. Okay, very good. Now you could have done this with water waves, anything that was a transverse wave, a rope, a guitar string, anywhere that energy is transferred. So a guitar string, plucking that string, you've got some kinetic energy from that finger applied to that string. The string vibrates, it imparts that vibration to the air molecules surrounding it, and then that sound moves throughout air. It dissipates, and then that energy has been transferred from one form to the next. Okay, this is question 20. I'll get you guys to have a go at this one. It says, identify a longitudinal wave type that is used in everyday life to transfer information from one point to another. Outline how the energy is transferred from one point to another using this type of longitudinal wave. Okay, so let's have a go at this one. 20. Okay, the better known one is a sound wave. So we're continuing with sound waves for longitudinal waves. And we're talking about information from one point to another. So sound waves created from a speaker. Okay, so what happens here, energy is transferred from one point to another using this type of longitudinal wave. Okay, so with the other one we talked about the electrons generating microwaves. Here we're going to talk about how we're going to make those sound waves. So with a speaker, what happens is, probably a diagram will help a little bit better. So you got some kind of magnet, and that magnet is attached to a membrane, and that membrane is three-dimensional, and it covers all that. It's almost like a cone, right? And then you have some kind of structure that's holding this in place, and then you got a bunch of coils that run back and forth like that, and they connect to some amplifier. So let's simplify that drawing a bit like that. Okay, so what happens is, as electricity is sent that way and into these wires which circle the entire magnet, and then go back through the other wire, magnetic field is created in that wire, which makes this magnet move up and down depending on the direction of the electric field. So what the amplifier is doing is sending those electric signals in different directions very, very rapidly. And when that happens, this magnet moves up and down very, very rapidly as well. And because it's attached to that membrane, it's getting pushed up and getting pushed down constantly by that magnet. And when it does that, the particles of air, which surround everybody, are also being oscillated up and down with respect to that membrane, with respect to that electric, with respect to this magnetic field that's created by the electrical current that is oscillating back and forth, that is generated by the electricity, which is presenting a sequence of pulses of electricity, which represents the music that was being recorded, or the voice that's speaking, right? So I guess you could send a pure tone, and if the tone was given by this wave, and say that was, I don't know, let's say that was 1,000 hertz, then that would be saying that there would be 1,000 oscillations, 1,000 cycles back and forth in 1 second to create that tone. So that membrane would be vibrating up and down 1,000 times because of all these different I guess parts that make the speaker, and once those air particles experience that membrane hitting against it back and forth, that propagates into space, or propagates through the atmosphere as refraction and compression waves, and they get to our ear, which is interpreted by our ear apparatus, and heard and translated into some kind of sound that we hear. But in essence, it's that. Yes, it's the speaker imparting that kinetic energy onto the air particles, and those particles push that kinetic energy back and forth, kind of like bumper cars, as until the point that it gets to our ears. Okay, let's have a look at 21. Identify the medium involved in the propagation of the following mechanical waves: a tsunami wave, a sound wave, an earthquake wave. Have a go at that, and we'll get back together and go over those answers. Okay, for A, the medium was water. For B, the medium was air. For C, the medium was earth, or some kind of silicate, or whatever you want to use to describe the earth. Okay, excellent. Let's move on to the next question. Okay, now this question is saying, students carry out a first-hand investigation of transverse wave traveling along a string. So that's quite interesting. So our setup is this. Somehow we got some kind of ends that are fixed, and we got a string is oscillating between those attachments. Okay, they collect measures of frequency and wavelength as shown in the table. Okay, so what they've noticed is when they are plucking it 11 times in 1 second, they're getting a wavelength that's generated a length of 0.71 meters. Very good. When they pluck it at a rate of 36 plucks in a second, so remember, it's how many waves are created in a particular time interval. So I guess a pluck is not the most accurate way to say it, but I guess if you're creating basically this in your string, in a pluck on wavelength, then that's kind of what we're doing. So we're saying we're doing 11 of those in 1 second, and we're getting a wavelength. So say we did get those 11, and we're saying that each one of those wavelengths are 0.71 meters. Remember, they've given us units of centimeters. Okay, so that's what's happening there, and they've plotted the data below, but the data is a bit weird. The data is a bit obscure because here we're given inverse units. So the graph is not wavelengths in meters. Remember, lambda is equal to wave length, and f is equal to frequency. And frequency in hertz, they're not giving us this data. No, they're giving us this data, which says 1 over lambda, and on the x-axis we got frequency. So that's weird, right? That's not right, and that unit is inverse meters. That's odd, right? But what we notice is when they do plot that, we get a couple of values that kind of form some kind of linear line. So we've talked about this before, when we have to do weird things to data in order for it to act in a straight line. So let's have a look. We'll get back to this, but let's have a look at this data looks if we were to plot it as it is. Okay, so just remember, guys, that I have a video online about how to plot data on Excel, but I'll use Excel this instance to demonstrate what's the pattern that's appearing there. Okay, so we got wavelength, wavelength. Our next column is going to be frequency. Okay. Now wavelengths are 21, 33. We do them in meters. 0.21, 0.33. Now I'll enter the rest in. Okay, so I've entered my data in. I'm going to graph this. So how I do that, I'll go to insert. I'm going to want a scatter plot. Sometimes it thinks it knows what you want. Usually does, but most of the times it doesn't. So click on your graph again. Go to select data. Remove everything. We want to add some data into it. We'll call that wave versus frequency. You're going to have, on the x-axis, you're going to have frequency. On the y-axis, you're going to have wavelength. So you plot that. That's okay. You can put axes and trend lines. We'll go with axis first. Okay, that's good. We can actually go back to charts. And we can modify this to have a line. Okay, and we can see this is what's happening. So this is problematic because, you know, that's wavelength, and that's going to be frequency. You can't figure out anything from this because it's got an odd shape. You'd have to use some pretty, okay, so you'd have to use some calculus to solve what's happening at each section of this weird curve that's happening here. But most important, like what I've taught you guys, is to see what what shape is being represented by the graph, and try and predict what it is. So in this one, quite interestingly, we can see that there's something that looks like this, and it's an inverse relationship. Now, that's saying as x, or the frequency, is increasing, the wavelength is decreasing. They're inversely related. So we can actually speed the process on Excel to prove this. So we can have another column. We'll call this 1 divided by wavelength. And if I plot this variable with frequency, I'm hoping to linearize it and get a straight line, which is what we have in the graph there. So this is quite interesting and quite easy if you get good with Excel graphs. So all you have to do to get a function to occur in Excel is you press the equal button. You start typing what you want it to do. So I want to divide 1 by something, and I want to divide 1 by wavelength. I hit enter, and it computes it for me. Now I can speed this up even more by just clicking on this green dot, and I can repeat that function over and over down there, down the column. So I've done that. Now I'll plot this. I'll insert a line graph. I'll select my data, thank you. I'll add my data. My x-axis is still going to be frequency. My y-axis is going to be something different. My y-axis is going to be 1 over wavelength. Okay, and there you go. I got my straight line compared to the initial graph. So you can see there is an inverse relationship. I've just proved it by taking the inverse of the wavelength. I've proved that. Now this question here is not asking you to do that. It's not asking you to inverse the data to get a linearized form. They've already linearized it for you. They want you to do something else. What they're asking is for you to draw a line of best fit, and then see what that line of best fit means, and then find the slope or the gradient of the graph. So let's do that. Let's talk about line of best fit. Okay. So if you look at all your data points, you got one here, 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 and there. With your line of best fit, you're trying to balance all those points out in some kind of form there. 6, 7, 8. Okay. And that's exactly what I'll do. So I'll try and get all of them as balanced as I can. And you see that kind of falls in the middle of all of them. You do your best. A lot of it is an estimate, and it's about doing your best estimate of that. Okay. And that's my line of best fit. So I've tried to balance all these errors and inconsistencies, and I've got my line of best fit. So that's done. Now it says take the gradient. We've spoken a little bit about gradients in tutorials. We haven't gotten to them. We have spoken a little bit in that first step study, and we'll talk more about them next term in our next topic. But the general expression for gradient was this. It's usually denoted by the variable m, and it's rise divided by run, or y2 minus y1 over x2 minus x1, where y2 is some point very far away in the vertical value. So y2 here, say my point is going to be the furthest most part here, y2 is going to be 5. That's my vertical point there. So let's do that. So y2 is going to be equal to 5. Now I'm going to do the whole line. I'm going to go all the way down there, make my life easier. So y1 at this particular point is going to be 0. If I chose to go with this point here, my y1 would have been 1.2468, so 1.4, right? But I'm just going to go with 0, so y1 is going to be equal to 0. Now my x2 and x1. So x2 at this vertical point is 38 hertz. Now remember, these are inverse meters. Okay, and my x1 is going to be 0. Okay, so let's do that. That's going to be, my gradient is going to be equal to y2, which was 5, y1, which is 0, x2 is 38, right, and x1 is 0. Okay, 5 divided by 38. Now remember, these are inverse meters. And that's hertz, right? Anyway, so we do that, we end up finding out that our slope is equal to 5 divided by 38 is equal to 0.13. Leave it at that. It's got some weird units, hertz per meters. That's a weird unit. We'll come back to that. So that's our slope. That's great. That's awesome. But it's also saying find the speed. So this is the second part that gets a bit harder. So let's have a look at that. Alright, so we've determined that our slope is equal to 0.13 hertz meters. We'll come back to what that unit is saying in a second. But how do we calculate speed from the slope? Now, if you had some kind of graph, say this point here was 2, and that went up that way, and say point here was 3, another point here was, let's say that was 4, and let's say here is 1, here is 2, here is 3, and right here is 0. We can define this graph, this graph. So the one that you guys have covered is this: y is equal to mx plus c, I think you guys use. So c is supposed to be the y-intercept, and where that line intercepts the y-axis is number 2. So c is equal to 2, right? X is equal to just the variable x, horizontal value, y is equal to vertical value, and m is equal to the slope. Okay, so x and y values are related by the slope and this variable here, c, the y-intercept. The slope of this one, we can find the slope of this one using our expression before, y2 minus y1 over x2 minus x1, right? So we're going to say our y2 is 4. We're going to say our y1 is 3. we're going to say our x2 is 2 and our x1 is 1. That gives us 1, 1, that gives us 1. So we got a slope of 1. So m is equal to 1. So we can find out any form of corresponding x to y value, so long as we put this condition in. The slope being 1, we have to multiply that by whatever x value that we choose, and we have to add 2 to that. So say I wanted to find out what would be the corresponding y value when x is equal to 2. Let's do that. I know it's going to be 4, but we can prove it with this equation. Y is equal to 1 times 2 plus 2. Y is equal to 4, right? So that's what's happening there. This is the equation that we're kind of setting up here. But going back to this, we don't have a y-intercept. Y-intercept is equal to 0, right? So let's start setting that up. What's our equivalent y m x plus c value? Okay, c is equal to 0. We got that. M is equal to 0.13. Now what's y? Y is 1 over wavelength. So that's interesting. Is equal to 1 over wavelength. And what's x? X is equal to frequency. Right? So let's rearrange this around, or substitute the appropriate variables for it. So let's have a look at that. So good. In order to get a corresponding inverse wavelength value, you have to multiply 0.13 by frequency, and it's plus it by 0, so we can get rid of that. So this is our general expression. But there's something unique about this expression, right? This expression is something you've already come across. So just remember, okay, 0.13 frequency. You've come across that before in this expression, right? Speed of a wave is equal to the frequency multiplied by its wavelength. We've just represented it as a graph here, and we've done some weird stuff to it. So how can we make this look like that? Like this. We will move frequency to this side, frequency to that side. Sorry, we'll move wavelength. We'll move wavelength to that side. We'll leave frequency on this side. We'll move speed to this side. So we're left with 1 over the wavelength is equal to frequency divided by speed. Alright, that's a bit weird, right? And now what happens is, this can also be expressed differently. This can be expressed like this. 1 over wavelength is equal to 1 over speed times frequency, right? Now this is what we got there. That's what's being presented. We're saying, yes, the general expression is y is equal to mx plus b, but here we don't have y is equal to mx plus b because we have different variables. Here we have 1 over wavelength is equal to 1 over v, and x is f in this instant. We don't have any y-intercept, so it's just plus 0. So that's quite interesting. Our slope is 1 over v. Okay, and we can prove that just by looking at the units, right? So remember how we had those weird units where it was hertz divided by meters, and what happened was hertz is remember that hertz is equal to the amount of wavelengths that occur over a particular distance in a given time, and because frequency is equal to 1 over period, where t is the period, f is equal to frequency, and remember, period is the amount of time for it to complete one oscillation from there to there. One wavelength is the time that we call a period. So that means if period is measured in seconds and frequency is equal to 1 over the time measured in seconds, then that's going to be 1 over seconds, right? So frequency has a unit of 1 of inverse seconds. So let's do that. That's saying that 1 over V is equal to 1 divided by meters 1 divided by, okay, 1 divided by seconds, right? So this is weird, right? This simplifies to this. That when you have a division between fractions, we can invert them together and multiply them. So 1 divided by seconds divided by meters, it's like writing 1 divided by seconds times 1 divided by meters, which gives us 1 divided by meters second. Okay. Okay. Now these units, something has happened here. With this previous example here, how I'm telling you guys that the slope is hertz divided by meters, that's not entirely true. Now if we look at the graph, it says inverse meters and hertz. So I've actually put those units the wrong way around. Those units should be written like so. Again, so we've got our equation set up. We're saying the y variables are going to be y over wavelength, 1 over wavelength. Our slope is going to be 1 over the speed of the wave, and the x variable is going to be frequency. We don't have a y-intercept, but let's have a look at this slope, at the units on the slope. So we know on the y-axis we have 1 over wavelength, and we know that on the x-axis we have frequency. These are the units. We know that frequency, hertz, is 1, it's inverse second, so we end up with this fraction. So in order to make this work, this is like writing this divided by 1 over s, which can be simplified by flipping one of the fractions around. So inverse meters times 1 over seconds. So we get seconds meters. Now that's the opposite of speed. Speed or velocity, speed slash velocity is equal to distance divided by time, which is equal to meters per second. Okay, so we have that inverse unit there. So because we have the slope m is equal to 1 over v, which is equal to 0.13, in order for us to get that value of v, we just have to take the inverse of 0.13. So let's do that. 1 divided by v is equal to 0.13. We take the inverse on both sides, so we end up with v on this side, and we end up with 1 divided by 0.13. We end up figuring out that v, or the speed of the wave, 1 divided by 7.6 meters per second. 7.6 meters per second. Okay. And that's the answer to B then. Okay, now 2 marks. These will get easier with time. You just have to remember that y is equal to mx plus b. That comes up so much, and it's just presented in different forms. Like here, it's presented in this form, which is whatever variable on the y-axis this instant is the inverse of the wavelength. The slope is presented as some different variable here. Instead of rather than m, it's 0.1, 0 divided by v, not 0 divided by, 1 divided by the speed. And the x variable is frequency. We don't have any y-intercepts, so don't have to worry about that. We'll talk more about this expression as it comes up in class, but this is a nice example that deals with that. Okay, let's move on. Okay, question number 23. Waves in the oceans often occur in sets. One set is sketched below. Surfers often describe the size of waves by the vertical arrow shown in the diagram. So the surfers describe it from the trough all the way to the crest. And here we've got one that's represented by 3 meters. Have a go at answering these questions and then come back to see how you went. Okay, A. Calculate the amplitude. The amplitude's half the distance between the trough and the crest. Here, the amplitude for A. Amplitude is equal to 1.5 meters. Calculate the wavelength of these waves. So we have one complete wave, 2 complete waves that occur in that distance. So yeah, from this point to the next crest, and from this crest to the next crest, you can see those are wavelengths, and therefore a wavelength, variable y, is equal to half of that, which is 12 meters. C. It says a surfer measures the time for the wave to travel 24 meters. So let's have a look at these unknowns. We have some distance denoted by the variable s, 24 meters. And it's done this in a time of 15 seconds. Calculate the frequency of these waves. Okay, there's a couple of ways that you can calculate this one. The more intuitive way is to figure out the period and solve for the frequency. So remember, the frequency is equal to 1 over the period of a wave. Now, if it's saying that the wave So it's saying that the surfer saw this wave from here to here, that particular wave move from its initial, sorry, this, not from here to here, move a total displacement of 24 meters in 15 seconds. That would say that the period is half of that total displacement. So the period would have to be half half of the total time, which is half of 15 seconds, which is 7.5. So that means we can solve this now. 1 divided by 7.5 is going to give me 0.13 hertz. Or you can solve it another way, which is you got a total of 2 wavelengths that have occurred over that 24 meters, and you know the time. So if you have 2 wavelengths, wavelength, and you divide it by the total time that is taken to complete those 2 wavelengths, 15 seconds. This gives you a rate. It gives you a ratio of these movements of wavelengths per second. That, in essence, is what a hertz is. How many waves are passing over a particular region in 1 second. This is what this is giving you, which is the same answer. 2 divided by 15, 0.13. Okay. D. So calculate the speed. So we can calculate the speed now that we have all these variables. We know that the frequency is 0.13. We know that the wavelength is equal to 12 meters. And we know that speed is equal to frequency times wavelength. So we find out that speed is equal to 1.6 meters per second. Okay, and lastly we have E. So E says, a little later another set of 3 waves arrive. In these waves, the distance from the crest to the trough is measured as 2 meters. So rather than it being 3 meters, it's measured as 2 meters. But they have the same wavelength. Alright, so they're still the same distance from there to there, from peak to peak. It's just their amplitude has been reduced. Predict whether the set carries more or less energy than the previous set of waves. Justify your answer. So by having that, amplitude's always got to do with the strength of a sine wave. The bigger it is, the more strength, the more intense it is. Here, if we have something that's 2 meters, then that intensity has decreased. Considering the wavelength is the same, the wavelength hasn't decreased proportionally with that. So, you know, it's not like it's got a ratio of strength similar to this big wave. No, because that amplitude has decreased, that strength has also the strength of the wave has also decreased. I mean, it makes sense as well if you think about those big waves at the beach that surfers jump on. That's a lot of force, a lot of power that's behind some of these humongous waves. It's taken a lot of displacement of water, either by wind or other form of volcanic terrestrial activity, to get that wave to be such so large, so much power to displace that amount of water. When it's 2 meters, obviously not as much power has gone to create that big wave. So therefore, having a smaller amplitude would indicate that that wave is less of power.